I would like to present you some results on measuring GNSS satellite transmit power. And let me start with the question why transmit power is relevant for precise orbit determination. The answer is antenna thrust. Antenna thrust is a small acceleration caused by the transmission of navigation signals by the GNSS satellites. The equation for this effect is quite simple. What you have to know is the transmit power P, the speed of light, and in addition the mass of the satellite. The effect that antenna thrust causes is primarily a radial effect. So you see here the equation for the radial effect, and in addition to the acceleration, it depends on the orbital period of the satellite. Currently, there is a IGS GPS transmit power model. This is based on minimum received power specifications as given in the interface specification of GPS and empirical scaling factors. One problem of this model is that there were inconsistencies regarding the atmosphere modeling when deriving these scaling factors, and therefore these scaling factors are too large by 1.5 dB. And in addition, there are no or limited data for the other GNSS, Glonas, Beidou, Galileo, and QZSS. Therefore, we have conducted a series of measurements with our 30-meter high-gain antenna at our ground station in Weilheim. You can see the antenna on the left-hand side, on the right-hand side, the ground station with some other antennas. It's a 30-meter antenna. It has a dedicated L-band feed with a total gain of the system of about 50 dB. The more detailed measurement setup you can see here. So after entering the telescope and the L-band feed, the signal passes a series of low noise amplifiers and bandpass filters, and then enters a vector signal analyzer and then the final analysis and storage system. It's a fully calibrated system to obtain receive power and spectrum measurements, and we use this to determine the transmit power of a series of GNSS satellites. When determining the transmit power, we need the so-called link budget. So you can see here on the left-hand side of the equation the received power. This is actually the measurement of the system, and this is composed of the transmit power. This is what we want to obtain. Then the gain pattern of the transmit antenna. You can see here an example for Galileo. So these are quite old published values from prototype or preliminary antennas. You see that we have some differences between the IOV and the FOC satellites, and also some differences for the different frequency bands. Then we need to know the gain of the receive antenna. So this is done by calibrations with a well-known radio source. And the major part of this link budget is the free space loss due to the large distance between the GNSS satellites and the receive antenna. And finally, we have some atmospheric losses depending on the zenith distance of the satellite. You can see here an example of the measurements for one particular Galileo satellite in the E1 band. So in red is given the received power, already corrected for the receive antenna gain, the free space loss, and the atmospheric loss. So the quantity that we measure is the effective isotropic radiated power, the AERP. And what we estimate is the transmit power. And this is essentially an offset between the gain pattern shown here and our measurements. So the green curve is just the gain pattern as seen here, plus the estimated offset, which is actually our transmit power. In this example, we obtained for the Galileo E1 band of this FOC satellite, for example, a total transmit power in this band of 120 watts. So the total power of the GPS satellites, you can see here on the left-hand side. We have one of the older Block 2A satellites with about 50 watts. Then the 2R satellites have a little bit more power. So these are the satellites that only transmit L1 CA code and L1 and L2 P code. We have a transmit power of about 150 watts for the Block 2RM satellites, in addition transmitting the L2C signal, and a further increased power for the 2F satellites, which also have an L5 signal. The consistency which within each block is quite nice with only a few watts, but only for the 2F satellites we have one particular satellite with a larger deviation from the others. So to compare these values with other measurements, we found a publication which is quite old, almost 15 years old, by Wu, and you can see here L1 transmit power values obtained from different sources. So in the different shades of blue you have pre-flight measurements done on the ground. Then the green bars represent onboard measurements directly onboard the satellite at the end of the high power amplifier. In yellow you see ground measurements with the Stanford antenna by Wu, and in red only for 2 of these satellites the ground measurements we have done. In general you can see a quite nice agreement on the level of a few watts, but you can also see that there are some discrepancies, for example for this satellite already between different pre-flight measurements. We can also compare our values with the current IGS model, so these are the solid lines in this block, in this plot, and you can see that there are some discrepancies. I've already mentioned the factor of 1.5 dB due to erroneous assumptions when obtaining the scaling factors, and this gets smaller, or we get some nice agreement if we correct for this 1.5 dB error. Then we have a quite nice agreement as shown by the dotted lines with our measurements. The results for GLONASS are shown here. Here the situation is quite different within individual blocks. So for the GLONASS M satellites you can see that there are large differences within each frequency. So essentially we can group these measurements into 3 subgroups on each frequency band of L1 and L2 with low, medium and high transmit power. You can see in blue the only GLONASS M Plus satellite, and in violet the 2 GLONASS K1 satellites. For K1 we have significant differences in the L3 band. There, one special feature of the first satellite is that this satellite uses a dedicated transmit antenna for the L3 band. The reason for these differences in the L1 and L2 transmit power of GLONASS M, we can only speculate. It might be related to failures of individual components of the amplifiers or of the antenna. And only for one satellite we could identify the time of these change in the power, and this is the first satellite here you can see with this quite small L2 power, and we found in the time series of C over and 0 values of receivers of the IGS network. We found on the 2nd of February 2015 a drop of 5 dB, so this was a permanent loss in the transmit power observed by several receivers of the IGS network. If we move on to Galileos, then there is also a well-known feature in one of the satellites, also a loss of transmit power as reported by Marco on Monday already 3 years ago. So the E104 satellite lost its capability to transmit E5 signals. You can see here the time series of C over and 0 of a receiver at Zimmerwald. So you can see here the drop in the transmit power of both satellites, and then afterwards we only have E1 transmissions. So before this event we have 2 measurements of the IOV satellites, which are shown here in green. So this is what I call here nominal transmit power of about 150 watts. After this event ESA lowered the transmit power of the satellites, and we have currently 2 different levels. So the first 2 satellites shown here in yellow have this status which is called all bands aligned with a transmit power of 130 watts. And the E103 satellite has a status which is called a temporary back-off with a reduced power of about 95 watts. For FOC, the general transmit power is higher, so we have here levels of about 260, 270 watts, and we have quite nice consistency within the different individual satellites of this group. For Beidou, we have, in addition to the MEO satellites I've shown you so far, also satellites in inclined geosynchronous orbits, the IGSO satellites, and here we have the problem that we have only low elevation data. So you can see here a sky plot of Weilheim. The MEO satellite in blue has a quite high elevation because one selects satellite passes with high elevation. But for the IGSO satellites, we have only elevations up to 25, 30 degrees. And you can see also here in this measurement plots that the scatter of the IGSO satellites is much larger and only a quite small band of the gain pattern is covered. So results are here shown on the right-hand side. We have about 180 watts for the Beidou 2 IGSO satellites, 130 for the MEO satellites of the second generation, and also we have observed 2 satellites of the latest generation MEO satellites with an increased power of about 260 watts. We've now introduced these transmit power values into a global solution to study the impact of antenna thrust on the orbit determination. You can see here the differences between solutions of half a year obtained with antenna thrust and without antenna thrust. So these are the radial differences of the different satellite groups. For GPS, we have values between 3 and 7 millimeters. So 2RM and 2F have quite different transmit powers, but they also have quite different masses. So the 2F satellites are much heavier, resulting in pretty the same shift. For Glonas, you can see a smaller effect as the transmit power also is in general smaller. You can see here the differences for the different powers of IOV. For the FOC satellites, you see 2 satellites where the radial change is smaller. These are the 2 satellites in eccentric orbit, so they have a smaller semi-major axis, and therefore also the effect is smaller. The largest effect for FOC and the satellites in higher orbit, so these are the Beidou IGSO and the QZS satellite. For QZSS, we could not obtain measurements due to the low elevation, but there is one published value in the literature we have used here. So this gives only an order of magnitude of the changes, but it does not say anything about the accuracy of the orbits, and therefore we have also done SLR validation, a quite old period, some years ago for GPS in order to cover the 2 satellites equipped with SLR reflectors, a more recent period for the other GNSS. In general, the biases are on the level of 2 to 3 centimeters, and you can see here the changes in the bias. So a positive sign here means that the magnitude of the SLR bias gets larger. A smaller magnitude is represented by a negative sign. So you see that for GPS, the bias gets smaller. For Glonas, some get smaller, some get larger. Galileo IOV gets smaller, FOC gets larger. So we have no clear picture if the SLR bias gets smaller in an absolute sense. However, you have to keep in mind that deficiencies in solar radiation pressure modeling have a large impact on the SLR bias. Just an example from JOVE-B, where modeling a plate connected to the satellite causes a bias of 10 centimeter in the SLR bias. So this could also be, the remaining biases could also be related to remaining deficiencies in solar radiation pressure modeling. So in summary, antenna thrust is a small effect, but it is one further step on the pathway to improve precision, and it requires knowledge about the satellite transmit power. Therefore, we have done measurements with our high gain antenna, resulting in general in transmit power levels between 20 and 280 watts. We have changes with time for Galileo IOV, and also one GLONASS M spacecraft. We have 6 subgroups of GLONASS M spacecraft identified with different transmit power levels, and the transmit power of the GPS satellites is in general smaller than for the current IGS model. The effect we have is 1 to 27 centimeters. However, we have still some millimeters. Centimeter would be a little bit too much. The uncertainties we currently have is for some spacecraft, the uncertainty in the satellite mass for Beidou and QZSS. For the GPS-2F spacecraft, we have only uncertain transmit antenna patterns. And for GLONASS and Beidou, we have nothing or only simulated patterns. So therefore, the support of the GNSS providers is needed in order to obtain the values for the gain pattern, for the mass, and also for historic data. And a regular monitoring of the transmit power is necessary, as there are changes in the transmit power from time to time.